Hello, my amazing algebra students. Today, unfortunately, I can't be with you, but we are moving on into lesson 6 in our book. So would you please open up your book to page 176. On the top of page 176, we've got these two different expressions. And if I was here in class with you, I would split up the class and have one half do one expression and one half do the other expression. Because I'm just doing this as a video, I don't think that we're probably going to try all 4 of these. But what I want you to follow along with right now is I'm going to put a 5 in for the n in each of these expressions and see what happens. So in the first one, I would have 5 squared minus 9 over 2 times 4 minus 3. Well, in the numerator, I would have 5 squared, which is 25. 25 minus 9 is going to be my numerator. In the denominator, I'm going to have 2 times 1. So I'm going to have 16 over 2, which is just 8. Right, showing a whole bunch of work. But when I put 5 in there, I get 8 from that first expression. In the second expression, I have 2 places to put my n. So I would have 5 plus 3 times 5 minus 3 over 8 minus 3 times 2. We have to make sure that we're following the order of operations. In the first parenthesis, I would have 8. In the second parenthesis, I would have 5 minus 3 is 2. In the denominator, make sure that you are following order of operations. 3 times 2 is going to be 6, so 8 minus 6 is going to be 2. And 2 divided by 2, I'm sorry, I didn't follow order of operations there after I said I had to. I would have 8 times, I think we can do that division, 8 times 1, which is going to be 8. Right? We could have also multiplied 8 times 2 would be 16, and then divide by 2, we get 8. Either way, I get 8 on both of these. And there's a reason for that. These two expressions, even though they don't look the same, they are called equivalent expressions. Equivalent just means that they are going to give me the same value. If I put in the same number for n in both of them, I get the same answer. Parts of this, you might even be able to see why that's happening. For instance, in the denominator, if I would distribute this 2, I would have 2 times 4 gives me this 8. And then minus 3 times 2, they left it as 3 times 2. Trying to trick us so that we couldn't see it, but that really does work. In the numerator of the first one, when I've got n squared minus 9, later on in the year, we're going to figure out that if I would multiply n plus 3 times n minus 3, which is something we don't really know how to do yet, but we will, that would give me n squared minus 9. So these two expressions are equivalent. They just don't look the same right now because they were trying to change up the just the basic look to try to trick you. So I'm not going to do all 3 of these. I'm going to talk about this statement right here. Do you think that the 2 expressions will have the same value no matter what value of n is used? And I'm going to say yes, they are, because we have equivalent expressions. They are going to be the same. If you don't believe that, you can certainly go back and try the other numbers that were there, but I promise we're going to get the same answer from both expressions each time. All right, on that same page, much ado about ages, we have this. It says, write as many equations as possible that could represent the relationship between the ages of 2 children and each family described. Be prepared to explain what each part of your equation represents. So in family A, the youngest child is 7 years younger than the oldest, who is 18. So I could, for that first one, just use numbers. I could do something like 18 minus 7 and figure out, oh, that really means that that child would be 11. Or I could have that same equation just kind of rearranged, if I know that the youngest child is 11, I could do something like 11 plus 7 equals 18, which is just a rearranged version of the first equation. Or I could say 18 minus 11, because I know that the child is 11, would be that 7 for that difference. I could also write these pretending like I don't know the age of the youngest child. If I didn't do this math to find this 11 right here, I could have this written as 18 minus 7 equals, let's say, the age of the youngest child. Or I could say the age of the youngest child plus 7 equals 18. I could also do 18 minus the age of the youngest child is that difference of 7 that we had. Okay? So those are all equations that I can write from this information. Part B says, in family B, the middle child is 5 years older than the youngest child. So I think here we're going to have to use two different variables. I used A for the age of the youngest child in part A, but let's use M for the middle child. And let's use Y for the youngest child. So if I have that, then it says that the middle child is 5 years older than the youngest child. So I could take the middle child minus 5 equals Y, or I could say Y equals M minus 5. I could also say that the youngest child's age plus 5 should give me the middle child's age. And if I would subtract the two, if I took the middle child minus the youngest child, that would give me a difference of 5. All right, so all of these are equations that work for the description that they gave us, right? And they're all equivalent also. They all mean the same thing. Consider the equations that you wrote for each situation. Are they all equivalent? Oh, I just said that they were. Sorry, I gave that one away. And what do you think it means for two equations to be equivalent? I've already said this a couple of times, but if they are equivalent, starts out looking like equal also, that just means that I'm going to get the same answer from any one of those equations, or the same value would make all of those equations true if they are equivalent. And if I put in a value that's not true, it won't work in any of them. Okay, so Tyler thinks that the relationship between the ages of the children in family B could be written as 2m minus 2y equals 10. So m is the middle child, y is the youngest child. That's how we had that. So I want to know, it says that he's right. I want to know why that's okay. If I've got this equation right here, take a second, try to figure out what Tyler did to one of our original equations to get this equation. Where would that have come from? Right? What Tyler did really is he multiplied one of our equations by 2. If I would take that equation and divide everything by 2, right? If I have 2m minus 2y equals 10, and then I divide this by 2, and I divide this by 2, and I divide this by 2. Kept everything balanced because I did the same thing on both sides of the equal sign, I would get m minus y equals 5. And that was one of the equations that we had to start with. Okay, number 3, are any of these equations equivalent to one another? So this is a totally new situation. This isn't about the ages of children or anything. Just take a look at these different equations that we've got, and I want to know if any of them are equivalent. Can you see, I'm hoping, how these two equations would be equivalent? What they did in this one is they really just subtracted 6 from both sides, and I would end up with 3a equals 9, which is that equation right there. Okay? Then, let's how the next one goes. That a plus 2 equals 5, if I took the original equation, so I'm comparing it to this one right now, and that one, can you see how those two equations are related? What steps did they take to get from my original equation to that a plus 2 equals 5? Well, I see that in the first one it's 3a, and 6, and 15. If I would divide everything here by 3, divide by 3, divide by 3, divide by 3, everything gets divided, I would get 1a plus 6 divided by 3 is 2 equals 5. And that's that equation right there. All right. The last equation that they have up there, I don't think that I would go all the way back to that first equation to get it. I would like to look at these two together. Knowing that I want that 9 to go down to a 1, and I've got a fraction with the a, it looks like I'm going to be doing a division. To get the 9 down to 1, I'm going to divide by 9, divide by 9. I would get a 1 on the right side, which is what I wanted, and 3 over 9 could simplify to just a over 3, right? Divide by 3, divide by 3. So that's how these two are related. So really, all 4 of these equations are equivalent, right? Sometimes we have to go from equation 1 to equation 2 to get to equation 4, but they are all going to be equivalent. They would all give me the same value for a if I would solve them. Okay, now this is on the bottom of page 177. It's called What is Acceptable? Noah is buying a pair of jeans and using a coupon for 10% off. The total price is $56.70, which includes $2.70 in sales tax. Noah's purchase can be modeled by this equation. So just talking through this equation, X is going to be the price of the jeans. Hard to read my writing there, sorry. So this is the price of the jeans. And then he's got a 10% off coupon. 10% as a decimal would be 0.1. Right? We move our decimal over 2 places, so 0.1. So that's saying I'm going to take 10% of the price. This is the discount right here. And then he has to pay sales tax. That's the $2.70. That's my tax. And we've got the total over here is the $56.70. Okay? So that's what all the parts of the equation are. Part A says, for this question, what does the solution to the equation mean in this situation? So actually, remember, if I would solve this, I would be getting the X all by itself. I would isolate the variable. X is the price of the jeans. So the solution to this equation would tell me the price of the jeans for this. Okay, and then it says, how can you verify that 70 is not a solution, but 60 is the solution? If I would substitute in there, I'm going to save us some time right now. If I substitute the 70 in for the X, what I end up with is, if X equals 70, and I just put that in there, I would get a price of $65.70. Well, that's not what it costs. They cost $56.70, so I know that 70 is not a solution. Then it says, how could you show that 60 is the solution? If I would substitute in, again, I'm going to try to save us a little bit of time, but I would have 60 minus 0.1 times 60 plus the tax of 270, That really does give me 5670. I promise it works, but you can certainly double check that for me. So we know that 60 is the solution. Now, if you'll turn the page, please, to 178, I've got that equation up there in blue is the equation that we were just looking at. It says each equation is a result of performing one or more moves on that original equation. Each can also be interpreted in terms of Noah's purchase. So for each equation, we want to figure out what they did, what the move was, and what it means, okay? And then it says we should check if 60 is the solution. Again, saving some time, I promise you, 60 is the solution for all of these, okay? So what I'm going to have here for equation A, they took, again, we're looking up at this top equation right here, this one. And they did something to it to get this equation. Well, it started with just a 1x, and now I've got a 100x. So did I multiply everything by 100? If I had 0.1 times 100, yeah, that would give me this 10x right here. If I took $2.70 times 100, I would get 270 and 56.70 in dollars times 100. That gives me this number. So what they did was they multiplied everything in the first equation by 100. And the interpretation of that, they even say it right there, the price is expressed in cents instead of dollars. If I multiply everything by 100, it changes dollars into cents. Will it give me the same solution? Yes, it absolutely will. It has to work because I just did the same thing to both sides of the equation. We're still balanced. Okay, for equation B, now I've got a new one here. X minus 0.1x equals 54. Some stuff is missing from that first equation. And what's missing is that they subtracted $2.70 from both sides of the equation. So what that means for my interpretation would be that's the price before they added the tax. Okay, and is it the same solution? Yes, it is. I just took $2.70 off of both sides. It's still going to work. Equation C, they've got 0.9x plus 270 equals 56.70. So they don't have two things with x's. What they did for this one is they combined these two x's. They said 1x minus 0.1x is going to be 0.9x, right there. So that's what this number came from. Everything else stayed the same. So what they did was they combined like terms. And that interpretation is saying that instead of having the original price minus 10%, well, when you take 10% off, you're going to be actually paying 90% of that original price. Instead of doing it in two steps, they're just trying to put it all into one step. Okay, now on page 179, I've got three more equations. And it says for each equation, determine what move was made or how the equation could be interpreted, and then check to see if 60 is a solution. And again, saving us some time. 60 won't be the solution. It's a secret. What was done in this one for equation D, and in your book you can still see the original equation in there, it looks like they just took the $2.70 off for the tax on the left side, but they did not do that from the right side. So they subtracted $2.70 from left, but not from right. Okay, we know about solving equations. Is it okay to do something to one side of the equation and not the other side? Absolutely not. That is not going to be a balanced equation anymore. It's not equivalent to my original equation. The interpretation that they've got here is that that's the price after using the 10% off coupon before the sales tax, but we didn't actually take the sales tax off of the right-hand side. So is it going to be the same solution? No, this will not. All right. For equation E, that $2.70 is gone also, and it says that they subtracted $2.70 from the left side, but they added $2.70 to the right side. So it's skipping the interpretation for a second. Is that going to be the same solution? No, you can't do two different things to the two sides of the equation. The interpretation for this is that that would be the price after the coupon and before the tax, but it's a different price now. So it's really a totally different equation. I'm just not going to take the time to write that out. For equation F, they have basically the same equation here, but they're going to do this right here. They're going to multiply this side by 2, but they did not do that on the other side. So they just multiplied the left side by 2, but not the right side. So the interpretation would be if you bought 2 pairs of jeans, that would make sense for that. But again, they didn't change what was on the right-hand side. They didn't double the actual cost. So that doesn't work. Will it give me the same solution? No, it does not. Question 4 says, which of the 6 equations are equivalent to the original equation? Well, the first 3 were equivalent. The second 3, 4, 5, and 6 were not equivalent. So I've got that separated here. Equation A, B, and C are on the left because those were all equivalent. And we had moves, we did things that were okay. So again, in equation A, we multiplied everything by 100, changed it into cents. In equation B, we took off the tax from both sides of the equation. In equation C, they combined like terms. We can do all of those things because we were keeping everything balanced. Equation D didn't work because they took the tax off one side but not the other. Equation E didn't work because they subtracted on one side and added on the other. And then equation F, they multiplied one side by 2 but not the other. If you don't do the same thing on both sides, it's not going to be equivalent, right? So we've got some different explanations here for what that could mean, but again, we just know that the ones that are equivalent would all give us a cost of $60 for the jeans, and the ones that were not equivalent would have totally different answers. Okay, this is not in your book, but I would hope that today if you were talking to somebody that wasn't in class and you were trying to explain what equivalent equations are, it's when you take an equation and you do something to it, you make a, let's call it a valid move. You do something that actually makes sense, and we're doing the same thing to both sides of the equation. It's not equivalent if you do different things to both sides of the equation. This example that we've got here, they start with this equation, 5y equals 6. So this is talking about buying 5 tubs of yogurt and it's going to cost $6. And then they want to know which of these are equivalent and which ones are not. So if I would take both sides of that equation and multiply them by 3, I would get 15y plus 18. I'm going to say, yes, this one is equivalent. That one's just fine. For the second one, they have the 5y matching, but the 6 got doubled to be 12. That is not equivalent. For the third one, they had 5y on the left and they added 4 to it. And then on the right, they had 6 and they also added 4 to that. Well, when I combine those like terms, I do get this 10 right here. So I'm going to say that the third one matches. For the last one, it looks like they took the 5y and they subtracted 1. But if I did the same thing on the other side, I don't get 3. I would get 5, right? So this one does not work. Okay, this is in your book. There's an example here that you can go through for what these mean, and please feel free to look that over if you want to have another example, but I do want to point out what I've got here at the bottom. It says, for example, if we subtract 50 cents from the left side but add 50 cents to the right side, the result is something different. It's not going to be equivalent because I did different things to both sides of the equation. All right, no, I was good there. Equivalent equations are equations that have the same solution, and then they're going to be called equivalent equations. We take valid steps to get from one equation to another equation. Today's homework is on page 182 to 185. Basically, you're going 1 through 9, and you're going to skip number 5. And that will be in Schoology. Good luck.